Welcome to ECE 302. This is lecture 4.5 on uniform random variables. I'm Professor Stanley Chen. Today we're going to look at one of the three very useful continuous random variables for this course. This is the uniform random variables. If you look at the schedule on this slide, you realize that we're now in the middle of chapter 4 on continuous random variables. So far, we have talked about the probability density function, the CDF, the cumulative distribution function, the expectation, mean, mode, and median of continuous random variables. The uniform random variable, it is a very special type of random variables that is very easy to understand because the PDF is just a straight line. However, using the uniform random variable, we will be able to see how all these concepts that we have learned so far be linked into a specific random variable. So today's lecture will focus on three things. We'll look at the definition of uniform random variables, we'll look at the properties of uniform random variables, and we'll look at some examples. To start with, let me define the probability density function of a uniform random variable. As you can see in this slide, the probability density function of a uniform random variable is defined as this two-case expression. In the first case, we see that this random variable x evaluated at a point small x is given by this number. Now, this number is not a function of x. It's just a constant. What is it? Let us draw a picture of this equation. Suppose that we have a point A and then we have a point B, as suggested by this equation here, where x is between A and B. When x is between A and B, we know that this function would take a constant line, is a straight line, okay, with a height of 1 over b minus a, which is given by this quantity here. And then where it is outside this range of a and b, then what do you have? You will have zeros. And when you are inside a and b, you will have this height of 1 over b minus a. So this is the PDF of a uniform random variable. It is a very easy to understand random variable because it's zero everywhere and it is a constant when you are within this range of a and b. So you may say that this uniform random variable doesn't really depend on x because this number here is independent of x. However, don't conclude too early because this x is actually defining the range of this support. Well, because if you change this a and b, the x that you can live would change. If you define the random variable x as this, you can also using this notation to say that x with a little snake and say that it is coming from uniform from this range of a and b. Now, this uniform random variable, as you can see, is specified by two parameters, a and b. A is the starting point and b is the end point. Now, is it going to be a closed interval or an open interval? That does not really matter. This is because for continuous measures, probability that x equals to a is 0. So you do not need to worry about the endpoints. Whether it is an open interval or a closed interval, since you're using a continuous measure, it does not really matter. Okay, so this is the definition of a uniform random variable. And let us look at a particular example and see if it makes sense. Okay, so this is the PDF of a uniform random variable. This random variable is defined as x drawn from a uniform distribution. The starting point is 0.2, the end point is 0.6. So we will draw a function as shown here. It will be 0 all the way until 0.2, and then you jump with certain constant, and then you go back to 0 after 0.6. Now we ask, what is the height of this uniform random variable? This is 1 over b minus a. And then what is b? B in our case is 0.6. So this is 0.6. And a in our case is 0.2. So you have 1 over 0.6 minus 0.2. So that's 0.4. And if you do the calculation, this is equals to 2.5. So you can see that in this equation, the height of this probability density function is indeed more than 1. And that's allowed because what you really want is that if you integrate your fx of x dx from 0.2 to 0.6, this has to give you 1. Okay. Now, if the number here, if the range is from 0.2 to 0.6, which has an interval of 0.4, then you know that the height of this quantity here, since it has to be non-negative, well, it has to be bigger than 1 in order to get this integral to 1. Okay, and so because you require the area under the curve to be 1, and this is less than 1, the width is less than 1, the height has to be more than 1. Okay, so this is something different from a probability mass function. If you recall a few lectures back, when we defined the probability density function, we argued that the PDF can indeed have a value bigger than 1. And this is a very obvious example using the uniform distribution. Now, on the right-hand side of this slide, I'm showing you the CDF, is the cumulative distribution function for this uniform random variable. Let me remind you, what is the CDF? The CDF of a random variable is the integration going from minus infinity up to a point that you're interested in. So let's say this is your x. You integrate all the way from minus infinity to this point. That will give you the CDF evaluated at x. And so that will give you a point somewhere here where this height will be the area under the curve from minus infinity up to the point x. Okay, so why is it a straight line? Okay, the reason is that the PDF that you have is a rectangle, and so as you move from the left to the right, you are uniformly increasing the area under the curve, and so that's why you will have a straight line. Now, if you wonder what is the equation for this CDF, here is the equation for the CDF. The CDF of a uniform random variable is given by this. It has 3 segments. When you have so you have A and B. When you are less than A, this equation says that it is always 0, and when this is bigger than B, it is always 1. Just to remind you that a CDF is a function that is monotonically increasing, or at least it is not decreasing, so it has to go up. It starts from 0, it goes all the way to 1. In the middle, when you have x between A and B, then this equation, you can write it as 1 over B times x plus 1. Okay, so this would define the slope. This would define the y-intercept, and so 1 over b minus a, 1 over b minus a. Okay, so the slope, so how do you know? Well, the slope is, this is the height. The height is always 1, and then the width is b minus a. And so if you want to draw a straight line, this straight line will have a slope of 1 over b minus a, and then the y-intercept, so you can trace all the way back. Because A is not necessarily 0, so you can trace all the way back to the origin, then you can find point. Okay, and this is a typo. It has to be minus A. Okay, all right, so this is the CDF. Now, how do we show that the CDF is given by this equation? Well, we can go through some very simple calculation. because the CDF is defined as the integration from minus infinity all the way to x of fx. I'm using t as a dummy variable, okay, so that I do not mess up with my x. Now, what is the PDF here? The PDF is 1 over b minus a dt. Okay, so that is the PDF of the uniform random variable. The question here is, should I integrate from minus infinity? No, we should actually integrate from a, because for anything that is less than a, you actually have a 0. Okay, and then you have x. So when you integrate that, you have 1 over b minus a, and then you have x, and then you evaluate the upper and lower limit. So that's not x, that's t. Then you will get x minus a divided by b minus a. So that will show you the CDF of the uniform random variable. All right, so let me show you some examples of calculating the probability using the uniform random variable. There are 2 parts in this example. The random variable x is assumed to be a uniform from -2 to 3. As always, I encourage you to draw a diagram so that you know what you're doing. This uniform random variable is has a range from -2 to 3, and in between it is constant, and afterwards you have 0. Now, inside this range -2 to 3, what is the height? The height is 1/5. The reason is that this is the interval, right? The interval has a width of 5, and so the height will be 1 over 5. Okay, so this is the PDF, and then we ask, what is the probability that x is between 0 and 1? So the probability that you have x is between 0 and 1, that thing is just integration from 0 to 1 of your uniform PDF, which is 1 over 3 minus 2, or if you like, this is just 5, and then you do the dx. Okay, and so if you substitute the numbers in, you have x. You need to evaluate from 0 to 1, so you get 1 over 5. Okay. Now, if you like to bypass this integration, you can also say that, well, the size of this set is just 1. The size of this set is 5, and so you have 1 over 5. So that's also allowed because this is a very simple random variable. Now, let us look at part B. Part B says that I want to evaluate x squared less than 2. I want to calculate this probability. Now, this probability is the same as the probability that x is between √2 and -√2. Okay, and so then you can do this calculation again. So you have -√2 to √2 of 1 over 5 dx, and so you have 2 times √2 divided by 5. So that would be your probability. Now you can also ask, what happens if I replace this by another number? Maybe I replace it by a bigger number. Let's say this is 4. Okay. Now what happens if you replace the 2 by 4? Then you have x squared less than 4. So that will give you what? So that is the same as the probability that your x is between -2 and 2. Okay, and so then you need to integrate from -2 to 2. Now, what happens if I change this number to 9? Then in this case, you have this 9 here, and then you have this 3 here, and then you have this 3 here. Then this probability is a little bit trickier because you're integrating this 1 over 5 and then dx. Now I ask you, what should be the range? Now if you write -3 to 3, that would be a problem because your x doesn't actually go from -3 to 3. Your x actually just go from -2 to 3. So this probability should actually be minus 2 all the way to 5, and you will get 1. Now you ask, does it make sense? Well, if you go back to the definition here, where x squared is less than 5, less than 9, then of course x is between minus 3 and 3. But since your x is between minus 2 to 3, this is of course has to happen always. Okay, it's not possible to have x that is living between minus 3 and minus 2. It just doesn't happen. And then you compute the intersection between this and also your sample space. You see that the probability has to be 1. Now, the uniform random variable that we have described so far are for continuous random variables. For the discrete random variables, you can also talk about the uniform distribution. In this case, the PMF is given by the equation here. Now, this equation may look a little bit complicated, but it's actually not too difficult to visualize. Let's say you're starting from A, you end up with B, and then it's discrete, so you have an impulse here, another impulse here, another impulse here, the last impulse here. Okay, so what is the number? Well, so you have this 1, you have 2, you have 3, you have 4. You have 4 of those. And so what would be the height? Okay, so because they're uniform, so they have to be the same height. Okay, now you say, okay, what would be the height? Well, because you're counting 4, and so the height has to be 1/4 each, because you're talking about a uniform random variable. How do you count? Well, it has to be b minus a. But if you just take b minus a, let's say you have 4, you have 1. Okay, 4 minus 1, that's only 3. You are missing 1 here, so you need to add 1 more. So that would be the number of stems that you have in this uniform PMF. And then the height would be 1 over that. Okay, if you're a little bit more careful, you can see that the range of k is going from a plus 1 all the way to b. There are actually b minus a plus 1 elements inside this interval. Okay, so one example would be to think about what if I have a discrete uniform random variable from 5 to 10. Okay, if that is the range, then the PMF px of k has to be defined as 1 over 10 minus 5 plus 1, so that would be 6. It's not 5 of those, it's actually 6 of those because you need to count the endpoint. The moment of a uniform random variable can be calculated as follows. Let's say your random variable x is between a and b, then the expectation, which is also the mean, is just the midpoint of the distribution. The variance is b minus a squared divided by 12. The proof of these are actually very straightforward. The expectation of x is just the integration from a to b of your x times your PDF, which is b minus a, and then you have dx. And so if you do the calculation, you have b minus a, and then you have 1/2 x squared, and then you put b and a. Now you do the calculation, that will give you b squared minus a squared divided by 2 times b minus a. And then there was some cancellations going on, so you have b plus a divided by 2. So that is the midpoint. The variance can be computed by first finding the second moment. The second moment is a to b of x squared of 1 over b minus a dx. And so that is b minus a of 1/3 x cubed of ba. And then that will give you b cubed minus a cubed divided by 3 of b minus a. And so that will give you a b squared minus ab plus a squared divided by 3. The variance of x is just the second moment minus the first moment square. So you have mu square. Mu is the expectation of x. So you put these two numbers in, okay, with a square here, then you can show that it's going to give you b minus a squared divided by 12. So I'm skipping the steps here, which I'm confident that you can fill this blank by yourself. Okay, so this is the moment, the first moment, which is here, the second moment, and also the variance. They are given by these equations. Finally, I want to talk about a very particular example of how to refine a transformation of a random variable, and then we want to find expectation. The technique is actually already discussed with you when we talk about the expectation, but I want to use this uniform random variable to do an illustration. So let's say that you have a random variable theta. It is distributed according to a uniform distribution from 0 to 2 pi. And then I'm defining a new random variable x, which is the cosine of omega t plus theta. Now, realize that in this equation, omega t is a deterministic quantity. It has nothing to do with your theta. It is not random, it's known, it's fixed. Just treat them as fixed constant. Okay. The only randomness goes with this theta. We want to find expectation of x, and we know that the expectation of x is just expectation of cosine omega t plus theta. And how do we calculate this expectation? And this expectation is the integration of cosine omega t plus theta, and then you will have a PDF of the theta and then d theta. And then we ask, what is the theta range? The theta is from 0 to 2 pi, as we have defined here. Okay. Now, if you forget about this equation, let me just remind you, if you have expectation of a g of x, this is the same as the integration of gx, and then you have fx x dx. This is the PDF, and this is whatever function that you want to put in order to calculate your expectation. All right, so that is the general principle. So let's carry on this integration. This integration is just the integration from 0 to 2 pi, and then you have cosine of omega t plus theta, and then times 1 over 2 pi. Now, why do I have this 1 over 2 pi? This is because your theta is uniform from 0 to 2 pi, and so this PDF is just 1 over 2 pi. Okay, or if you want to be more explicit, it would be 2 pi minus 0, 1 over the end point minus the starting point. So that you have this 1 over 2 pi here, and then how do we continue? Well, you have integration with respect to theta, and now this will give you 1 over 2 pi. Oh, wait a minute, this is actually easier, right? Because it is a cosine function. It's a cosine function, so we can first of all draw the cosine function, and then you can integrate this cosine function from 0 to 2 pi. You just integrate this thing. What do you get? Well, you get 0. Why? Because when you integrate cosine function from 0 to 2 pi, you integrate in the entire period. You have plus and you have minus. They cancel out. And so this will give you a 0. It doesn't really matter how you shift this theta, because if you shift the theta to the left, to the right, it is still a cosine function. Okay. It also doesn't matter what your omega t is, because by having a different omega t, you're shifting it to the left or to the right. So in any case, when you're integrating one period, you will get 0. So that is the expectation of your x. The x is given by this number 0. The main key here is to recognize the first equation, where the expectation of a function is just the integration of that function value times the PDF. And then you integrate with respect to your random variable. Okay, so I want to summarize today's lecture by using this slide. We have learned about the uniform random variables. The PDF is given by this equation, the CDF is given by this equation, and we have gone through an example looking at the expectation. You may ask, when do we need to use the uniform random variable? I'm giving you 2 examples here. The first example is to model the quantization error. Okay, so let's say you have some random signal, and then you want to quantize the signal. by just sending fewer bits. Okay, so now you are constructing a quantized signal. You are always whenever you do the quantization, you have error, and these green areas, they are known as the quantization error. And people have found the quantization error can be well modeled by a uniform distribution. So in the compression community, this uniform random variable is widely used. Another example that uniform random variables are used would be to generate random numbers according to an arbitrary PDF. This is something that we will learn about in the later part of our course, but the idea is we always start with a uniform random variable, and then we do a transformation, and then the transformation will allow us to transfer all these random numbers to an arbitrary PDF. So being able to understand the uniform random variables, knowing their statistics, will be extremely helpful when we go to that part of our course. So this is the end of today's lecture. Thank you very much for watching. If you have any question, let me know. Feel free to post your questions on Piazza, and also try our homework problems. Thank you.